Good afternoon. I'm Chris Hansen. This is Jerry Sussman. We're going to be talking for 10 hours starting today. And let's sort of give you a little background on what we're going to be doing here. I've known Jerry for, close to 30 years now. We've been working together for all that time. We started off hacking on Scheme together. And well, we've gone to a lot of other places, but we're not going to be talking about Scheme today. We'll be using Scheme mostly because it's just easy for presentation, but we're not going to talk about it. What we're going to talk about is something that comes from a class that we started teaching at MIT about three years ago? Four years ago. Mm-hmm. And we were both involved in a couple of fairly boring classes before that I don't even want to tell you what they're about. They were not worth having done, let's put it that way, and the students got a raw deal out of it. But the interesting thing that came out of this is that in both of those classes, we started talking about some ancient technology from the 1970s, which no one knew about. Some very interesting things that we're going to talk about in this class. And the students perked up when Jerry gave a couple of talks about these things in those classes as demonstrations of things that would be useful for them to know for other purposes. And the students really responded to this material. And since at the time, Jerry was still fairly depressed about 9/11, and he needed something fun to do, I pushed him into teaching this class. And I basically said, look, we have all this stuff that people invented that has been forgotten. Let's warm it over and sell it to new people, you know? We can pretend it's new. So we started teaching this class, and it's been a lot of fun. We've learned a lot of things. And in addition, this resulted in some new work that we're going to get to towards the end of the week, the last 2 days of the week. But mostly what we're doing is we're going to be talking about programming, and in particular about how not to get screwed by programming yourself into a corner. Okay? And that our claim is that since between us we have over 80 years of programming experience, the claim is that we have been screwed over just about every way you can be screwed over. And we've learned ways to avoid getting screwed over, and we're going to try to convey them to you in the course of this 10 hours. And then at the end, we're going to reward ourselves by talking about something that we find exciting, which is the new stuff, and we're going to ask you to help us basically by giving us a hard time and making us justify what we're telling you. So, without further ado,
is this internal or external talk?
This is an external talk. We're not going to be doing anything proprietary here. And assuming the videos and the teaching come out well enough, we will be putting this up out at external-facing server. The video is being recorded. Okay? And that's it. So, Jerry, take over.
Well, I'm going to give you first a little summary of what we're thinking we're going to talk about in the next 2 days. We're going to talk about things that everybody knows a lot about, like generic operations, but most people don't get as generic as we will. They're going to be generic enough so that it's going to be dangerous. The nice thing about generic operations is that they give you a certain kind of additivity. However, the danger is that if you use generic operations a little bit wrong, you can cause yourself trouble, and I'll show you examples of that. However, there are some great powers associated with generic operations. For example, it's possible to obtain translucency from a opaque procedure. It is possible, for example, if you have something which is appropriately opaque, but you can't read the insides of it, of course. But if you can change the fundamental operations that it's made out of so that they can process different data types, you can in fact use them to, for example, give you a description of the result of running partial evaluation, and you'll see that. Okay, so that's one thing we'll talk about.
But you could inject stuff into these things and probe their insides.
Exactly.
Cool.
Okay, so that's one thing we'll see. Another thing we'll see is the power of building language layers, where you have one language on top of another. And of course, languages are the crucial thing you'd be building when you're trying to understand and work on hard problems. What you do is, rather than attempt to make whatever horrible language you have fit your problem, what you really want to do is build a language appropriate to your problem. And the reason why that's true is because when you build a language, it means you're going to represent and specify many similar problems with the same structure. So you'll make a mix and match pile of pieces that will be possible to put together in many ways and solve many related problems, thereby preventing you from getting yourself screwed by over-constraining your problem, okay, by solving this particular thing in too tight a way. Okay, so that we'll talk a little bit about that. There are various ideas involved in that. One thing we will then later do around, I suppose, almost Thursday, is talk about propagators. And I've brought along Alexei Radul, who is now running a doctor's thesis about these things. Propagators he'll talk a bit at that time. Propagators are a way of breaking free of expression structures, so that they no longer constrain you in the way that almost all the languages you've ever played with are organized around expression structures. Okay, and we'll talk about that some. And finally, if we make any real progress, we may talk at the end about the ways in which control can be distributed. Okay, so that we can have the question of whether you're pushing information through something or pulling information out of it. Okay? And so that's the overall structure I'll talk about, but I want to get into the material almost immediately. So Chris, can you flip me into this other, I don't understand Macs, okay, and I was nowhere near one before, so I have to apologize. It turns out that the world didn't like, so now we're going to talk about generic arithmetic, okay? Yes, generic stuff. That's, okay, well, you're going to have to put up with parentheses in this little set of talks. And part of the reason for that is the language we're going to be using, which is a variant of Lisp, is just easier to express all of the things I want to express that'll fit on a projection slide. Okay? You will see later, for example, some reasons why that's true, but that means we're going to be using prefix notation. That means I have an operator and some operands, and indeed I get a value by an evaluation process, and that's pretty simple. I'm sure you shouldn't worry about that. But the important thing to see here is that addition in some Lisps, in fact almost all Lisps, is generic of various kinds of numbers. So 1 plus 2 plus 3 is certainly 6, and 2/3 and a half is 7/6. Okay, and 2/3 plus 1 is 5/3, so you've just seen the 1 turned into 3/3. So then, we also have things that are using inexact numbers and exact numbers. An assumption that a floating point number is inexact, which no doubt it is because I can't specify it to full length. So that's 2/3 plus a half written a different way. And of course, sometimes we lose precision, we find that out. Okay, so that's just different kinds of simple generics. But what can you do? Well, once you have generic operations, there's some value to that. Let's talk a little bit about the value and the danger. Okay? Well, one problem is, of course, that things aren't exactly what you think they ought to be. If I make an inexact number out of an exact number, and then I make it back into an inexact number, an exact number, I come out with something which is different from the 2/3 I started with. Okay? By a little bit, but by golly, that's somewhat of a problem. Okay, the square root of 2 squared is not quite 2, of course, and things like the magnitude of 3 plus 4i is certainly 5, but the angle of 3 plus 4i is some long number. If I take a polar combination of those, I should get 3 plus 4i, which I don't quite get. So we all know that these are some of the minor problems of floating point arithmetic. Okay, but of course, what that means is that if you've written some program that assumes that things are exact, and then you happen to have an inexact extension of the operators, and you try to use it, maybe you'll get the wrong answer. Okay? And I want to be very careful about this. It is very important to realize that sometimes almost the right answer is the right answer. That's why floating point works at all. okay? That if you care extremely that something is provably correct, okay, you're in real trouble. Okay? And one of the problems with the way we write programs most of the time is we worry so much about things being correct that often we write things that are very, very narrow in their applicability. Okay? Because by golly, we can prove, to ourselves at least, I'm not talking about a formal proof, we can prove that the little algorithm we wrote is actually correct. Okay? Now that leads to very, very brittle structures. Because if everything's made out of little narrow, precisely specified pieces that all hang together in exactly the right way, and you build some pile of them, and you've got something on the top which is the answer to your current problem, and then you varied the problem slightly, the whole thing falls apart. Okay? So in fact, of course, digital engineers have figured out a way to solve this problem. Okay? There's this thing called the digital abstraction, which I suppose many of you know about, okay? Which is that you have some sort of, supposing I want to talk about some sort of objects like the kind you have in digital electronics, okay? Something like an inverter. Well, it has to have an input-output characteristic, V in, V out, that looks sort of like this. Okay, and it has to have the feature that there is the input things I'm allowed to take in are of a larger range than the things I'm willing to put out. Okay, so that for example, this will put out better zeros and ones than this is willing to accept. This is willing to accept things that are worse, and as a consequence, noise is suppressed. Digital abstraction. If every part in some system is willing to accept worse inputs and produce better outputs, then you get a certain kind of noise immunity, and that's quite analogous to what I'm talking about with respect to making things that are more general. So one of the advantages of having generic operations, okay, is that yes, indeed, there are some problems, but supposing I wiggle my system a little bit, it may do the right thing. Now, you may say that's a danger, of course. Supposing we have an air traffic control system or something, okay, or worse than that, an autopilot. Do you want an autopilot that's not specified to be absolutely right? Yes. Okay? And the reason why is that sometimes something bad goes wrong, like some control wire breaks. Now, what a good pilot does is he figures out some other way to fly the plane and often can land it safely. Okay? However, if the thing says, oh my gosh, I violated my assumptions, crash, well, it will crash. Okay, so it's very important to make systems that actually have flexibility, even in the face of it being slightly dangerous to be flexible. Okay, so so I'm talking about here. Here, let's take a look at use of these generic operations. So this is a program in this language, Lisp language called Scheme, and I'll read it to you because you haven't read them for a long time, many of you. Okay? Yes, somebody asked me how many parentheses can I stand here, and you're going to have to see a few. So this is the sigma, the sigma of mathematics. Okay? Sum over a pile of things. Sum of a function from low to high. So this is S sum of f of I given I equal low to I equal high. Okay? That's what this is. And it just says, this is the conditional. If low is greater than high, then the answer is 0. Otherwise, we're going to have a little loop here, which counts from I going up, from 1, and until I is greater than high, and the sum that starts at f of low, and it adds them up by going around the loop over and over again until it eventually returns the sum. How that works, that's its business. Okay? But anyway, having things like that's pretty nice. I could say the sum of the procedure of one argument, which is that value itself. Lambda of x is lambda calculus. Lambda of x, something like some expression in x, the sum of 3 and x, is the procedure that adds 3 to x. Okay? For those of you who haven't seen that. Okay, so this is the famous Gauss question. What's the sum of the numbers from 1 to 100? It's 5,050. What's the sum of the squares from 1 to 100? Well, it's 338,350. Okay, that's very nice. Why would I care about generic operations? Well, terrible way to compute pi is by adding up some interesting series. Okay, this happens to be a terrible way. I'm going to add up 100,000 terms of a series which is 4 times 1 minus 2 times the sum of the over n of this function, where this function is 1 over 4n minus 1 over times 4n plus 1. Okay? And indeed, this produces an approximation to pi, a lousy one. It's not the best way to do it, of course. But here's where you're seeing some of the dangers of generic operations. Over here I have a point, and here I don't. This was an inexact number. It forced everything to be inexact. Inexact numbers happen to have very small representations. Exact numbers can get arbitrarily large. The first 10 terms of this series, it produces something that's that big. If I went to 100,000 terms, it wouldn't fit in the universe, counting all the atoms. Okay, it turns out. I would have more digits than atoms in the universe. Okay, so that just shows an example of the danger of generics. Okay? But of course, once I'm allowed to extend my generic operations, wild things can happen. Okay? You see, and here's the place where I'm deviating from history. Okay? I'm going to allow my addition operation to be extended by some magic process, which I'll show you later what it looks like, but a magic process whereby I can now lift this to things like vectors over the reals. Okay, so I can have now addition, a scalar multiplication. Okay, but if it's two vectors, it's dot products. Okay, something's happening here. This is pretty interesting. That's pretty useful. We can go further. Gee, there are matrices. Okay, and if I can extend this arithmetic to deal with matrices. So matrices, two matrices added together gives a matrix. Matrix times a vector gives me some vector. Vector divided by, an extended division so that it's a left multiplication by the inverse of its second arguments. Okay, that's a choice. You may not like the choice. I don't like it either, but I did it just for fitting on this transparency. Actually not. I actually use it that way. I feel embarrassed. But okay. Okay. But you see, it's even better than that. Okay? Because there's no reason why all of the standard things we do in mathematics can't be thought of as appropriate generic operations. So, we have a cosine procedure that's built into some system. There's cosine of 3. Sine of 3 is another number. Gee, that's not surprising because 3.14 would have cosine 1, right? Minus 1. Right? That's the negative real axis. The sum of the cosine of 3 and the sine of 3 is some number. Well, we happen to know that the way mathematicians often write is, f plus g applied to x is f of x plus g of x. Okay, that's a choice people do a lot, and there's no reason why that shouldn't work either. So if somehow we have procedures which are the implementations of functions, we may as well be able to add them as well. And there's no reason not to. We just have a rule for that, which somehow we're going to describe by some generic operation extension, in which case we now can talk about the sum of sine and cosine. And indeed, we could talk about not just the ones that are built in, but any one that I type in. So the procedure of one argument x, which multiplies x by x by x, that's a cubing operation, okay, surely can be added to cosine. And if I apply that to 3, well, let's see, cosine 3 cubed is 27, and cosine is minus 0.0, so that's the correct answer, okay? So you see, that's a nice thing to be able to do too. But magic has not begun. Okay, this is only minor magic. Here begins to be some real magic. Okay, we'll do some automatic differentiation. Automatic differentiation is a process people use to compute derivatives in complex numerical processes. But it turns out it's actually, and I'll explain in a little while how to do that. Okay, and then it's going to be interesting. But I'm just showing you right now the generic extension. This is going to be turn out to work as a consequence of the fact that I can make generic extensions. In other words, the way I'm going to differentiate some complicated composition of functions is by making a special data type object, which is differential object, which if I shove it into a function, will somehow produce its derivative. Okay? And that's something that's a really special extension of the primitive operations such that they will compose appropriately and do the right job. Now, does anybody have any questions about this before I go on? So this is a kind of derivative. Okay, I'll wait for the answer. Are there any questions? Even people in Colorado? Okay. Okay. So this one's actually pretty interesting, right? Because what's happening here is, first of all, this is a derivative of the cosine function. We're talking about a derivative as being a different thing than the kind of derivative you learned in elementary calculus. Okay? In elementary calculus, you learned about expression derivatives. You learned that the derivative with respect to x of cosine x is minus sine x. Okay? That's a derivative. That's the derivative. Oh, I wrote it in Lisp. Isn't that interesting? Okay. 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 I have my parentheses always in Lisp mode. Okay. It actually turns out to have some advantages, which is that for very long expressions it's easier, and for short expressions it's harder to write prefix rather than infix notation. But in any case, what's going on here is this is an algebraic expression. It is not a function. Okay? This is an algebraic expression. It is not a function. A function, this object is the function. That's the cosine. Okay? Or the minus sine object is a function. So this is the application of a function at a particular value, which is unspecified. Okay? So what we're talking about here is the derivative operator that's used in modern mathematics, derivative of cosine, which is a new function. That function, when applied to x, gives me equals minus sine of x. Okay? That function applied to a is minus sine of a.
You can only apply it to a function that takes one.
No, actually, it turns out you can generalize this if you look in. By the way, the one you have here is generalized, but if you look in Spivak's book called Calculus on Manifolds, you get the full description of this kind of derivative. Okay, it's in an early chapter. I can't remember which one.
But your notation here assumes.
No, I have made no such assumption. Okay, because I said nothing about how many arguments that function takes. Okay, in fact, to be perfectly honest, let me show you something. Okay, the derivative of the procedure of two arguments x and y, which is the product of cosine x and sine y. That applied to let's see, this is, right, let's see, 1, 2, 3. Yes, that's the product. Then I've got the lambda, the derivative. Excuse me, it's not chalkboard. I'm much more used to chalkboards. Okay? Applied to, say, A and B. Okay? What is this? Okay? What this turns out to be is, I'll give you a mantra. The derivative of a function is a new function which, when applied to arguments, produces an object which, when multiplied by an increment in the arguments, produces the best linear approximation to the increment in the function value. That's the actual mantra. And therefore, as a consequence, this object had better be a structure containing the partial derivative d0 of this function. Let's call that f of f at a and b, okay, and d1 of that function at a and b. That's the partial derivative of the function with respect to the first argument and the partial derivative with respect to the second argument, such that this, when multiplied by something like a delta x and a delta y, will give me this times delta x plus this times delta y. Okay, does that answer your question? That's the ultimate generalization of derivative, okay, for functions from r to the m to r to the n. Okay, so this is beginning to play a little bit, and I'm just showing you that derivatives, okay, make sense. Okay, and then of course the second derivative of cosine is, well, this is interesting. multiplication for functions was slightly different from multiplication for derivative operators. They're a different kind of thing. Okay? Now, you would know that a derivative operator is a function on functions that gives me functions, but it happens in the traditions of mathematics that the square of a derivative is not the same thing as the square of cosine. Okay? The square of cosine is cosine of x times cosine of x, whereas the square of derivative is the second derivative of. Okay? It's derivative of. This is part of the unfortunate history of mathematics. We've got all sorts of strange notations in mathematics. Cosine square x is cosine x times cosine x. Cosine to the minus 1x is not equal to 1 over cosine x. Go explain that to a ninth grader, and you'll understand why nobody understands mathematics in the United States or anywhere else in the world. Okay, it's a obscure, crappy language. Unfortunately, Lisp works so much better. It's so much more consistent. Okay, but at any rate, but we're trying to capture the mathematics here. So I'm just showing you this stuff. So then, just as verification that this gives the right answer, and the derivative of cube, which is 3x squared, applied to 2 is certainly 12. Okay? So let's see. And we can also extend things to have units. Okay? Units are pretty useful. Units in dimensions, actually. For those of you who are electrical engineers, of which I suspect there are a significant number here, you recognize the charge on an electron, okay, right over there, 1.6 times 10 to the minus 19th coulombs, a strange unit, but one that's valuable. And then there's Boltzmann's constant over here, okay, which is 1.38 times 10 to the minus 23rd kilogram meter square divided by Kelvin second square, per Kelvin second square. So I suppose that must be really kilogram, I suppose that's speed. That's right, meters per second squared. Okay, that's another way to think about that. But here's the interesting thing. Supposing I have a famous algebraic expression which all of you electrical engineers have seen, kT over Q, right? The Boltzmann's constant times the temperature divided by the charge on an electron. How many millivolts is that? It's 26, right? Or 1 over that number is 38, which is the exponent in the diode law. Okay, that's all your transistors work that way, all your bipolar transistors. And by golly, it's possible to get volts out of that. Okay, now that's very nice to have such an extension possible. For the people who are not electrical engineers but may remember their classical mechanics, you know that that there's a Newtonian constant, which is the force of gravity. It's a very small number. So at least well measured constant among the physical constants, because it's very, very hard to measure. That times the Earth mass. What I want to do, supposing I want to figure out what it takes to move a 1 kilogram mass 1 meter on the Earth. I want to lift 1 kilogram 1 meter. How much energy does it take? Well, I have to take the force times the distance. I have to do an integral of that. Okay, so the force here is the Earth's mass, the product of G times GMM over R squared. Okay, that's what that is. Okay, this is the radius of the object from the center of the Earth, whenever I'm lifting it, and I'm going to integrate it from 0 meters to 1 meter. Okay, and by golly, it's 9.8 joules, which is the right number, because you probably remember that the acceleration of gravity is also 9.8 meters per second squared. Okay, so this is just giving you a feeling for that sort of advantage. And if you play the whole thing right, you can have even abstract quantities, things that are not, we don't know it's algebra, stuff we don't know the name of. Well, we don't know is a name for it. We don't know its value. Okay, so for example, we could have abstract A, which when added to 1 gives me 1 plus A. X minus y times x plus y is x squared minus y squared. The derivative of x cubed is 3x squared. Derivative of the cubing operation applied to A is 3a squared. Okay, correct. Okay, And indeed, we can mix all these things together and say that derivative, when applied to a certain number of kilograms per second, okay, is going to be the right thing in units. Okay, so that's giving you a feeling overall for the power of generics, as well as some of the dangers. Are there questions yet? Yes, sir.
So given that thing with the quoted A there, it looks like you're not doing this numerically, you're actually taking the derivative symbolically in all cases.
Well, I'm taking the derivative somehow, and we'll tell you about it in a little while.
Okay.
How's that? I'm not going to, it's not quite symbolic, and it's not quite numerical. It's better than that. It's being done by a generics, okay? In fact, what's happening, you're already seeing a little of it, that all that happened here is that the plus operation has been extended so that if its inputs are somewhat symbolic, then it does nothing other than const itself on, make an expression. There is a simplifier built into PE which prints it in a certain way. Okay, the result. That's all that is. So this is doing the subtraction is producing a difference. This is producing a sum. This is producing a product of the difference and the sum, and then this is doing the rearrangement to get it in that form. Okay, that's all. Okay. Now, derivative is doing nothing more, and I'll show you in a while, is doing nothing more than shoving an interesting kind of object through these functions. Not a symbolic object. It's a different kind of thing. Okay? It's a kind of number, actually. It's hyperreal, right, turns out. Okay. Okay, so let me just, before we get to that, let's actually talk about how I specify these things. This is rather easy in a kind of Lisp, okay? I'm going to show you how to, I'm not going to show you the details of the mechanisms. The mechanisms are ones that if you want to know about, we can publish a code for you to play with and work with. But basically, there are the default scheme operations, like I'm going to say the binary operation for addition is a generic operator of arity 2, and I'm going to make it default to be the systems version of addition. So unless I expand it, it's the system version. Unless the expanded version, unless I kind of catch this unless I'm going to have a special version of the operator that's appropriate for particular problems, particular types of things. Okay? So this is, now I'm also going to make that into a many argument procedure, because I like my addition to say the sum of 1, 2, and 3 and get 6, rather than have to decide what order the sum is, although that might get me in trouble someday if I'm doing floating point. How many of you realize just how bad floating point is? Okay? All right.
Floating point is not that bad.
Of course, okay? But a binary floating point is not actually terrible at all. According, that's the 754 standard is a big deal, which made it actually reasonably plausible. But if you have decimal floating point, all sorts of hell breaks loose. Did you know that?
Actually, a lot less hell than you think.
I'll demonstrate one that you probably haven't seen. Okay? What is the average of two numbers between the numbers?
Not necessarily.
Thank you. He knows. Okay? Here. 994 plus 996, is that what it is? What's the sum of those two? 9. What did I do? Did I just do anything? 998 I won. 996 plus 998. 996 plus 998. Is that right? That's 1994, right? Yes. Okay. Divide that by 2. That gives me, well, you see, if I only have 3 digits of precision, this gives me 995, which is not between the two. In other words, if I have a 3-digit, if I have 996 times 10 to the 0, times 998 times 10 to the 0 is 1994, which is 199 times 10 to the 0, 10 to the 1, right? Which is equal this times 10 to the 0. Okay? So therefore, the average of two numbers in decimal like that is not between them.
This isn't place to argue it, but
But nonetheless.
We'll give it a shot anyhow.
Yes, it is.
there are two features of floating point which ameliorate that.
Yes.
Okay?
Hidden.
The first one is that the result of the floating point operation is supposed to be the value, the closest representable value to the value you would have get if you had done it to infinite precision and then turned it.
Yes, of course.
Okay.
Okay.
Second thing is that if 996 and 998 are representable, then your answer would have been 996.
Well, I don't think that. I think these are all representable in three-digit floating point.
Right, but you're using a broken floating point model where you're not.
Okay, let's argue that one later. Well, I'm trying to tell you, the fact that we can have this argument is telling you there's something difficult here. Okay? That's fine, okay? I use this to freak people out. That's okay, okay? I actually think floating point is very, very important, okay? I worry about it a lot because I actually do celestial mechanics type things from time to time. Okay, and go rather nuts occasionally. Okay, so here's some typical handlers for these things. Okay, so here's supposing now I wanted to extend extend addition and multiplication. I'm going to extend multiplication to cover vector operations, scalar multiplication, for example. Okay. Well, I need one for scalar product. That's so I have the product. The binary operation for multiplication is a function of two arguments, the scalar and the vector, which makes a new vector. The length of that vector, which is for each element, the scalar times that element of the other vector. Okay, and that works for numbers and vectors in that order. Okay. However, if I have vectors and numbers, I have to declare a handler that says that vector times scalar, and it's the same thing, basically. And if I happen to have two vectors, okay, then the product of them is a dot. I'm going to interpret it as a dot product today. I might decide differently. That's up to me how I want to interpret it. I could be an outer product, for example. Okay, in which case it's the sum over the number of the length of the vector 1. Now, if I were being an honest man, I would write here the assertion that protects me from passing in two different length vectors, okay, by saying that vector 2's length has to be the same as vector 1's length, but I didn't have enough room on the projection slide, I assure you. So I deleted that nice line from my code. Okay, but in any case, this is for two vectors, gives me a dot product. Okay? Okay. So this is just showing how you do this sort of thing. Now you asked about derivatives. Who was the person who asked about derivatives? Good. Okay, that's right. Several people did, I think. Well, let me show you what the idea is. Supposing I want to take the derivative of a function f. Okay, I happen to have a function that maps from, say, reals to reals. I'm taking the simplest case. This is the simplest case. Okay. Well, I can always take that and make that into an object like a complex number. You know, x plus iy, x plus dx. Okay, is what this thing is. Dx is a sort of typical increment. There's a special kind of number called the differential. Okay, and I can map it to that, pass that through f, get the derivative of that plus this is f of x plus the derivative of f times dx. Okay. I can then consider only this result, because this is, in fact, a new object of the type this is. You see, if I interpret plus as being something like complex addition type objects. Okay? Okay? So this is being mathematical right now, and so I can pull that out and I get the derivative. Okay? Now this is true for every primitive procedure. Okay? It's true for cosine and sine and all the things I can extend every one of those to deal with that. And then I have to do clever things like extend addition and multiplication, but those are for two argument functions. Okay? And maybe arctan, which is a two argument function, things like that. Okay?
Question.
Yes, sir.
Small d here in the operation.
No. This is pure math type stuff. This is the
Constraint dx is
no. This is just no. Okay, it's actually explained over here better. Okay? This is one way to explain the idea. Okay? Here's a better way to explain the idea. I have an ordered pair of two numbers instead of one. Okay? This ordered pair is a differential object.
Is there a constraint of dx?
Is it?
Is there a constraint of dx?
No, it's just
It could be anything.
this could be any old numbers.
Well, dx is a,
It could be, well, usually I put it in one.
Yeah.
Okay? But it doesn't matter. Because derivatives are linear, and as a consequence, the size of that doesn't matter. Okay? Hang on. Okay, so here's what happens. So supposing cosine is extended so that if it sees an object of this shape, a differential object, which contains an argument for the cosine, and a differential part, I'll call it an infinitesimal part, okay? Then what it produces is a new such object, which is the value of the function as expected, plus the value of the derivative of that function at that place, times the differential object. That's a new differential object. Okay? Now, supposing I take this object and shove it into G, just to see how it works. Right? Well, what happens is the same rule. This became the x, therefore I get g of f of x, and the derivative of g applied at f of x, because here I have derivative of f applied at x, times, of course, the derivative of f at x times the dx. Okay? Oh, the chain rule worked. I got the real honest chain rule out of this because this is the correct chain rule if I take out the dx, if I map out the dx again. Okay? This is the correct chain rule because it's evaluating at the right place. Okay, so this is a way of using a generic operation extension to compute automatic derivatives correctly. And it doesn't matter what these objects are. These are numbers. Okay? If this is a number and this is a number, I'm getting numerical derivatives and it's correctly computing with the chain rule correct. If I have symbolic objects there, well, it does that too, because that has to do with the symbolic extensions. But they all interoperate correctly. Okay? So there isn't a question of whether or not I'm not doing symbolic manipulation. That's not the key thing. It's not that there's a set of rules of the form, if the thing is a sum, then it's the sum of the derivatives. Okay? It's that the sum procedure is doing something special with objects of this differential type. Okay, has everybody got that? Okay, that's a nice idea. I'm sure many people have had it. The way this got invented in my context was that Dan Zuras from Hewlett-Packard and I were sitting around I was on sabbatical at Caltech in 1991, and Dan came to visit me, okay, and spent a week with me because he's a guy who designed chips, and he in fact designed the chips we used in the digital orrery. He designed the floating multiplier and floating adder chips. And he came and hung out with me for a week, and we decided to write some derivative code, and we just spent a whole week thinking about it, and he came up with this with me. Okay, it was just fun. We sat there it took a long time to think that out. Okay, apparently, I'm sure a zillion people have figured this out. I'm sure there's no great invention. Okay, so here's more details of the insides. Okay, so you can see the handlers. Okay, just to give you a feeling for what it's like to make this kind of code. Okay, so I have the sign function for derivatives, the derivative handler. See, go down to the bottom here. The handler for sign is the sign handler for differentials going into it. Okay, the sign handler is over here. It's a unitary operation with sine as the function and cosine as the derivative of it, of the function. Okay, the unitary operator abstract function is the thing that takes a function and its derivative and produces a new function, which is also a unitary operation, which picks out the finite part of x and adds f of the finite part of x to the product of the derivative applied to the finite part of x multiplied by the infinitesimal part of x. That's all. You see? So that's actually, I'm giving you the code that does this. Okay? So, and similarly for cosine, just to see that again, cosine's got its own handler. Okay? And cosine's handler is that it's the cosine function with the derivative being minus the sine, the function which computes minus the sine. Okay? So this is sort of showing you true power that you can pull off if you have generic operations. Okay? I'm not going to show you the binary one because it doesn't fit on a single slide. Okay? But I'll show you vaguely what it's like. See, here's binary. The binary one, the insides are excised just because, you know, it's too big. Okay? It's a longer story. Okay? But let's take a look at what multiplication is. The binary multiplication operation is the handler for multiplication, binary multiplication is diff : star, takes two differentials in, okay? There's also coercions and things, as you always expect, which is differential and number and differential, all those other things have to exist. Because really, generic operations are really just a way of organizing a table of all the operations that can be there, okay? And what happens here is it's the product of the differential binary operator. Yes, the differential handler for products is the thing whose function is the product and whose derivative with respect to the first argument is the second, and the derivative with respect to the second argument is the first, the partial derivatives. And that's all I have to hand in here. That's what that is. Okay? You know, and all this code is free, so I can give it to you. It's no problem. Okay, you can have this code is available. We teach classes with this stuff, and it's probably 1,000 pages of stuff like this. Okay, accumulated over. Some of it's very embarrassing because it's really cruddy. Okay, however, okay, that's the story on generic operations from my point of view. Chris wants to say something more about these things now, having something to do with Java.
I'm going to do the really embarrassing thing.
Go ahead. Okay.
Can you repeat or summarize the dangerous aspects? What are
The most important danger is that you can build some system that already has built-in dependencies on special properties of the objects you already have. So, for example, I might have some big, complicated numerical thing that depends upon commutativity of addition. And then all of a sudden I say, gee, I wonder if this works for matrices. And the answer is, it'll come out with an answer, but it'll be wrong. And you don't know it's wrong unless you've tested correctly. And I believe in testing. Okay? How's that? More now than I did, also.
He's been putting the Kool-Aid into
Right.
Jerry's drinks.
Right. The testing Kool-Aid.
Okay, so I'm going to show how painful it is, but it's still possible. Okay, it's still possible, and it's actually not as bad as it might seem. If you're used to programming in Java, as I've become, it's not as bad as you might think to add this kind of clever stuff to a Java program. For the sake of, I've had to trim this thing down quite a lot. So in order to get an example that would fit on slides, I had to start with something really trivial. Okay, and so the trivial thing is that suppose we have some sort of an arithmetic class like this one here that knows how to do the basic 4 operations, and you want to add something clever like symbolic stuff to it, okay? And the symbolic stuff is helpful partly for debugging, and I'll show you an example of why that's helpful, but it's also helpful for if you want to do any sort of clever compilation. And we're going to see some more of this later, probably on Wednesday, I think. But you can, it turns out that if you have symbolic representations of things, you can use those symbolic representations to inject them into your program, and you can use the output of the symbolic stuff to make an efficient compilation of something that otherwise would be buried in layers of abstraction. Okay, so in other words, this thing that Jerry was talking about of making things translucent will allow you to do clever compilation of stuff that doesn't, without having to do any symbolic manipulation at all, particularly. You don't have to rewrite your program, you don't have to compile the Java, You just inject this stuff and you can spit out something useful that you can then process. Okay, so let's suppose we have this thing. It's got 4 operations. I can't imagine that anyone here would have any trouble reading this. That's too bad. So here's a transformation, beginning of a transformation. So in order to make this work, the very first thing is that you have to take this value class and you have to abstract it, and then we're going to subclass it. Okay? And at the very top level, we're going to make the fully general symbolic representations. We have these operations that catch the general case. Okay? And the general case basically is that when you get any kind of a value, you're going to combine them into some sort of, basically this is an expression. Okay? We have a compound literal, which is a symbolic expression that says plus of the 2 arguments, or minus of the 2 arguments, something like that. Okay? That's the general case. We then take the original number value thing that we had before. Let me see if I can get this to fit a little better. There we go. And we're going to have to we have the same code near the top, but now we have to write these special operations. And it turns out this is very complicated, mostly because of weaknesses in Java. Okay, Jerry and I, maybe there's somebody here who understands how to do this better. I do not. So what happens here is that we want to add some value, some arbitrary value, to the thing that is to this instance. And we have to, what we're looking for is the case where we're adding 2 numbers, numeric values together, because then we can do a numeric addition, and otherwise we're going to do whatever the default is. Okay, and in order to do this in Java, the method here is going to be selected at compile time, but we need runtime information. Okay, we can't determine whether this, we originally tried writing 2 methods in the forlorn hope that the right one would be selected, but it turned out that that doesn't work in Java because it's not defined that way. Okay, so this is, all of this verbosity here is just to get around that one little problem. Okay, and basically you fill in the rest of these operations. All the rest of it's the same. You do these operations, they override the symbolic thing. You put in a couple of other things. Here's a literal variable. Okay, here is the compound thing, which actually has no operations because the generic ones take care of it. Okay, and then we can write a little demo. Okay, here's a clever, well, not so clever, but here's a way to do exponentiation. Okay, using the standard 4 things. And this is sort of I like to summarize this thing as you take the exponent and you encode it as a bit stream, and then you basically multiply in the shifted base as you walk down the bit stream. Okay? That's sort of what this thing is doing. But this basically will compute an exponential, and it does it in log n time for the number of bits in the exponent.
Log n multiplications. The time
Correct, yes.
Thing is very large numbers.
Yes, log n multiplications, but I think it might be the same thing. Okay, so this thing will do that, and then we can run this testing, of course. So we can do it with some numeric things, and we can also do it with some literals. And what comes out at the end is that we can either get the numeric values of the exponents, or we can get symbolic ones, which are a little clumsy. We could reduce them a little bit. There's ways of making that better. But you can see the structure here. And one thing you can't see is the sharing. That this, for example, this times xx and that times x are in fact the same one, which is why you get the log n time out of this. Okay? But you can think of this as a way of looking at, this will show you in a very visible way that your algorithm is in fact doing what you think it's doing. So you can think of it as a kind of a debugging mechanism in this case for how you would go about, you verify that exponential, which is a bit hairy, and I wasn't even going to try to explain how it worked here, but that it's making the steps that you think it ought to be making. Okay? And what I didn't do, but what I could have done, is that if we knew, let's say, we know the exponent, we could have spit out Java code at the end. Okay, now that would have been a lot more slides and a lot more stuff, but you could actually spit out fragments of Java code and glue them together and then compile that, and then you have something specialized for a particular exponent. Okay? And in this case, that's not interesting, but in a more complicated case, It can be, and we're going to show you some more complicated cases later. Okay? That's pretty much all I had to say.
We have time for a 5-minute break, and then we'll talk about more stuff.
Okay?